Okay. So our linearization idea is that the function here could be very complicated. You know, this looks kind of like a polynomial, but it could involve some very complicated calculations. And so the idea of a linearization is that if I'm looking at some point, say A, I can approximate the function near A with a line. And the best line, or the best approximation, it turns out to be the tangent line. So I'll say that here in words. The best linear approximation to f of x at x equal a is the tangent line at x equal a. So if you want to have something close as possible to the function at a point, and you want it to be linear, the best option for you is the tangent line. And that shouldn't be a surprise. That's in some ways what we think of as the tangent line, right? It's like this line that's very close to the function right at that point. All we're doing in 310 really is sort of changing what we're doing with it. Right now we're thinking of that as being something that's going to give me values close to the function. If we call this tangent line, let L of x equal the tangent line, it's a function, right? Just a linear function. So we could call it L of x. Then L of x is approximately f of x for x values close to a. Clearly, if we're looking at x values way out here, the line is going to give me y values that are very different from the function, right? So it doesn't work all over, but as long as we are sufficiently close to a, the line and the function are pretty close to one another. Now, there are other approximations. Sometimes a linear one is effective. Sometimes you need a quadratic or a cubic. There are like raising degrees of polynomial approximations. But polynomials, it turns out, whether they're linear or quadratic or other, are very easy for us to work with in calculus, right? A derivative of a polynomial is your favorite kind of derivative, right? None of this chain rule or product stuff, right? It's just very straightforward. So it is handy for us to have approximations to functions because it can be much easier for us to work with. So that's the kind of theory behind this. And it turns out the execution of this is nothing we haven't done already. You did some of this on the exam. If you want to find the linear approximation at a point, you're just finding the tangent line at that point. It's the same question. I guess instead of letting y equals mx plus b, we replace that with L of x equals mx plus b. That's sort of convention. L of x is the linearization, but it doesn't really matter. It's the same relationship. And of course, if you want to write this down using the point we have here, the point is a f of a, and the slope, of course, is f prime of a, right? The derivative at that point is the slope of the tangent line. So we have the point and the slope, and you just put that into your formula here. L of x minus f of a equals f prime of a times x minus a, right? Y minus y1 equals m x minus x1. And then if you move the f of a over, I think the book writes it like this, f of a plus f prime of a times x minus a. And it sort of looks like it's like a new formula to remember, but it's not. It's just the tangent line at this point. So I would argue you don't really need that formula at all, but that's, if you look in the book and see that, that's where it's coming from. Okay, so it asks for the linearization. You just find the slope of the tangent line. And then of course it might ask you to approximate the function. And so what you would do there is you'd say, well, if I want to approximate it at B, right? Well, I just plug B in. L of B is going to be pretty close to F of B. Now, approximation is a really important part of mathematics as well. If you took a numerical calculus course, you would do a lot of work with computers and approximations, and it can be very complicated to figure out how good of an approximation you have, right? It's one thing to say it's pretty close to the function, but I'd really like to know how close it is, right? And so there's some analysis you can do there to figure that out, but we don't get into that at this stage of the game. So this is like the first half of 3.10 is like using the line to approximate the function values, right? I want to know what the height is at some point, the y value, the function can tell me, but the linearization can also tell me what that is. Any questions about that first half?
So is the linearization essentially like shorthand for a function? So before we're going into depth about finding out these different attributes of a function, whether it's a polynomial or a quadratic, we use the linearization just to sort of like, oh, here's like a rough guesswork essentially of like what it is at around this point.
Yeah, I mean, it can be really nice because a line is like so easy to work with. And so it's the idea that like if I have to think of the function, the easiest way would just be a line. And that's the linearization. But it turns out that as we look at the second degree or the quadratic approximation and the cubic approximation, and we start to work with those, let me back up a second. The linearization for us is not all that useful because it's like, well, why wouldn't you just use the function, right? You can just plug the number in and it spits out a value. In some sense, I can get it directly rather than approximate it with the linearization. But what happens is as we look at these successive approximations, so like this is the linear approximation, a quadratic approximation maybe would look like this, right? That's an x squared approximation. And maybe if I did a cubic approximation, I could line it up so it looked like that, and a degree 4 approximation, maybe I could make it look like that. And I can get closer and closer and closer to the true function. And it turns out that if you continue taking these approximations and you look at the limit of those, you can prove that it is equal to the original function. So in some sense, what this linear approximation is like the first step on this idea of turning a function into a polynomial. And that's actually pretty powerful because if you can take a function that's hard to work with and rewrite it as a polynomial that's easy to work with, you can do a lot of things that you couldn't do otherwise. That process is called power series. And you'll work with that if you move into Calc 2. So I guess that's a long answer to your question. I think you're kind of getting at the idea like how useful is this? What is this really doing for us? And my answer would be like not that much really right now, but it's kind of setting the stage for thinking about approximating functions or using polynomials to approximate functions. I don't know, did that, maybe that led to more questions and confusion, but it's like opening the door a little bit, right? And then seeing what's back there, and maybe we'll just shut that door for a little bit until we are ready to really walk into that. So I think there are some big ideas here. I also think it is a very, in this section, presented very straightforward in that if it asks you for the linearization, you're just finding the tangent line and using that to approximate the function. The second half of the course is actually, or of this section, is actually a very similar idea, but instead of approximating the function value like we did with the linearization, we're going to approximate the change in the function. So let's let delta y equal the change in the function over some x interval called delta x, right? Delta's change in physics, I guess, right? And so we use that notation here. So the idea there is that maybe I have a function and it goes from A to B. This distance is delta x, and there's a corresponding change in the function here, which we're going to call delta y. So in order to do that, you could, plug in b to your function and plug in a to your function and then subtract those two, and that's going to give you exactly what delta y is. But we can also approximate delta y by something called a differential. And the idea of the differential is if I look at this point A and I find the slope of the tangent line, remember the slope of the tangent line is always the rise divided by the run, right? That's what slope is. What we have here is we have this rise and this run, and visually you can see that this rise is somewhat related to or close to the actual change in the function, this delta y. And of course, as we get closer, as our interval gets smaller, that change is going to be even closer. Right? This sort of triangle is even closer to the actual function. So this value here we're going to call dy, which is the differential, and this delta x we're going to call dx when we use this differential notation. So it turns out that delta y, the actual change, is approximately dy, which is the differential. In the same idea here, right? That I guess I have it flipped around, but the idea is that we're approximating the true change with this differential. The slope of this tangent line is going to be f prime of a. Right? That's the slope of a tangent line to the function. And the slope of that tangent line is going to be equal to dy over dx. I mean, that's the definition of the slope of the line. And so what we can do here is if we want to find out what dy is, we just multiply both sides by dx, and we get a definition here for the differential. Dy is equal to f prime. Now, just to keep our kind of notation consistent, rather than fixing that at this a, which is kind of specific to this example, we use a generic kind of x. So this is the definition of the differential, dy. And you could come up with that, I guess, if you needed to, but it's this one I'm kind of like, we should probably remember that formula. It's kind of safer to do that than to try and come up with it. The tangent line one is something we've done a lot of, and so I don't think you need the formula for that one. Again, if you use it, great. But the differential one, we're not going to use that much of, so you'll just want to write that down. And again, it's just a calculation. So if they tell you, approximate the change in the function f of x, whatever it is, x cubed plus 3x minus 2, from x equals 2 to 2.1? Well, if we're going to approximate the change in the function over this interval, we're going to use this differential dy. We're going to notice that dx here, which is the change in the x, is 0.1. That's how far those are apart. And the slope is going to be f prime of 2. All right, so I'm going to look at 2. I'm going to look at the change approximately from 2 to 2.1, and my formula says that dy, that change, is f prime of 2 times dx, which is 0.1. And we could go through this, right? F prime of x, a nice polynomial here, right? 3x squared plus 3. So if I put in 2, what do I get? 4, 12, 15. So dy is going to be 15 times 0.1 equals 1.5. So again, there is an important idea here that we're using the derivative and slopes to approximate something going on with the function. But we don't spend a lot of time with this, and so you can be quite successful by just kind of remembering or focusing on those formulas. Questions about this part? And then we'll finally be ready to take a look at that question. Okay. So the question was that you have a cube, and the edge of the cube is 15 centimeters, but of course there's some always error there. The error is 0.4 centimeters. So I measured 15 centimeters, but it could be off a little bit. Use differentials to estimate the maximum possible error, the relative error, and the percentage error when we compute the volume and the surface area. Turns out if we get one of those, we're well on our way towards getting the others. And so what I want you to imagine is that, you know, this side is like x, right? And the volume of a cube is then x cubed. So if we think of that, that's a function, right? X cubed looks like this. And, you know, this is not the scale, but 15, right, is out much further. It's quite large, right, if you put in 15. But there's a little bit of possible error, right? It could be above or below 0.4 centimeters. It turns out when you're using differentials, because it's a line, it doesn't actually matter if you go above or below. It's going to give you the same kind of estimated change, right? Either above or below. So we'll just keep it above to kind of be consistent. So what is that? 15.4. That's going to give you a different volume, right? So this is the error, let's call it delta V. That's the actual possible error in volume. And hopefully when you look at the graph like this, you can start to see how differentials apply to this situation, because we have a function and we have a little change or displacement in x, and we want to know what the corresponding change or displacement in the volume is. And we can approximate that, right, by using our differential. In this case, this, whatever this value is, right, that's our dy. The actual change is approximately dy, and dy is f prime of 15 times the change, which is 0.4. So what's f prime? 3 times 15 squared times 0.4. I don't know what that is, right? Some number, some fairly large number actually, right? So even though you have a relatively small change in the measurement, it can lead to a pretty, it feels like a sizable change in the error. Now the problem is, you know, whatever this number is, 15 times 15, right, is 225 times 3, 675. I don't know. So what is something like 500, let's say, or no, it would be less than that. 250. I don't know what it is. Right. Some number, something like that. And this is measured in, well, this is, turns out this is going to be, it's going to turn out to be, what are we, centimeters, right? Cubic centimeters. So that feels like a big value to me. But the question is that actually a big value? And it sort of depends. Oh, someone 270, I believe you, that seems reasonable. I trust you more than my mental calculator. And to me, that seems like a lot, like 270 cubic centimeters seems sort of like a lot of cubic centimeters. But that's kind of like asking the question, like, is $1,000 a lot of money? Well, it depends, sort of, right? Like if it's my monthly income, $1,000 is a big deal, right? Very significant. If it's part of the $1.9 trillion stimulus plan, I mean, $1,000 like dust, right? It's inconsequential. There's nothing to that. So that's the idea of like saying that the answer is 270 cubic centimeters of error doesn't really measure the actual error all that much, right? If this is a small item, 270 cubic centimeters could be really big, but if we're talking about a stadium or something, nobody cares about 270 cubic centimeters. So that's what these secondary questions are. It's looking for also the relative error and the percentage error. So relative error would just be, you would just take the 270 and divide it by the total volume. Like what's the volume of 15 cubic centimeters? And you divide those, right? That would relate it to the original. And then percentages, you just change that to a percent. And that's really a better measurement of what the error is, right? If you just say the error is 270 cubic centimeters, it's not all that useful. But if you say the error is, the percentage error, the relative error is 0.4%, I say, that doesn't sound too bad, whatever it might be. Does that help? Does that answer that question? It's a very long answer.
Yep. It's all good. I appreciate it.
Yeah, and the surface area is the same thing, but it's just a different formula. But it'll be this very same, instead of F, you'd have some G, right? Some formula for surface area. And I do think when you have these application problems, it's sort of nice to write them using like a function notation, because that makes it easier for us to apply the ideas of the differential. That's kind of how we're used to seeing them. Okay, so as you work through the homework, you'll see there's some differential questions, which you'll use that little formula for differentials. And there's some linearization questions, right? Or L of X questions where you'll, find the tangent line and use that to approximate the function. Okay. All right, so I think those are the two ideas from 3.10. So let me take the next 15 minutes here and try and introduce the big ideas from 4.1. So I think you'll find, like, when you look at the the exams, or the ideas from 4.1 certainly flow through the whole rest of chapter 4. The 3.10 is its own little discrete thing. We don't really use it in other sections in this course in Calc 1. But 4.1 is setting the stage for the rest of the things in chapter 4. And it's very important that we understand relative versus absolute extrema. So extrema just is max or min. Like, rather than saying max min, we say extrema, or we say max min, but extrema sounds better. The plural. So there's some definitions here, relative versus absolute extrema. So when I think about a function, like this, so this is defined on a closed interval, there are some kind of points that seem important if I'm thinking about minimums and maximums. So sort of these points I'd be kind of interested in if I'm concerned with extrema. And so the easier one is probably the absolute extrema. Maybe I should label these A, B, C, D, and E. So the absolute extrema, there could be a max and there could be a min, and we are interested in both, sometimes what they are, but in many ways we're more interested in where they occur. So, you know, I don't think we need complicated definitions here. It looks to me like the absolute max occurs right there at B. So the absolute max is at B, and it's equal then to f of B, right? The function value at B. The minimum here occurs at E, and it would be equal there, right, to f of E. So in absolute extrema, the rule is it has to be, if it's going to be the max, it's got to be bigger than or equal to any other value. We also have here what are called relative extrema. And I do go into these in more detail if you watch the lecture capture and even maybe the short recorded videos. So I'm kind of skimming over these ideas. There's a little bit more to them, but a relative extrema basically means you have to look on both sides. You're interested in what is it close compared to its neighbors. Is it bigger or smaller than its neighbors? Then it counts as a relative extrema. So some of these are pretty clear that they're relative extrema, like B, C, and D. At those values right there, the function is bigger than anybody around it. It's not bigger than everywhere on this interval, so it's not an absolute max, but it is a relative max. This one is the same thing, right? Over a little neighborhood, it's bigger than everybody else, so it's a relative maximum and also an absolute maximum. So it can be both. This one here is a relative minimum. These values, it turns out, are neither relative maximums or minimums. They're not relative extrema because they're endpoints. I can't compare this value to both sides because the function stops there. So you can't have relative extrema at an endpoint. Get a relative max at B and D and a relative minimum at C. And we will use sometimes local is the same as relative, just a matter of I don't know what day of the week it is or something, right? We use those interchangeably, relative and local. The big distinction there, of course, is that relative extrema, we need to be able to look at both sides, and absolute extrema is just any value. And there can be sort of more complicated situations here. For instance, let's say we have a function that looks like this. Let's stop it there. So the question here I might ask would be, is there an absolute maximum? And you would identify this point, whatever it is, let's call that A and f of A. So the absolute max is f of A. Right? And of course, that's at x equal A. Right? That value is bigger than or equal to every other value of the function. So it's an absolute max. What about an absolute minimum? Can you see that for this function, there is no smallest value because of this asymptote? This function keeps going down, 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 down. So there's no absolute minimum. Does not exist. How about a relative maximum? Remember, for a relative maximum, you just need to be bigger than your neighbors on both sides. So you can see here, this one is certainly bigger than its neighbors, right? Both its neighbors on either side are down here. Doesn't have to be a very big neighborhood. It's just got to be bigger than everybody on both sides for a little bit. And this one certainly is. So relative max at x equal A. About a relative minimum. Don't get fooled by this point, right? That's an endpoint. That can't be a relative min or a relative max. And these values, again, because they keep going down, 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 there's no point where we're bigger or smaller than everybody else. So this one has no relative minimums. So it's may seem like a kind of simple idea like max and min, but it is more subtle. There are situations where it's not always clear, or it doesn't look maybe like what you think it might be. There are situations where we don't have relative minimums or absolute minimums or maximums. And we also want to remember that absolute minimums and relative minimums, or extrema, let's say absolute extrema and relative extrema, they're different things. So like sometimes they line up and you have an absolute and a relative min, let's say, but you can also have them be different things, or one not exist and one does exist. So they're really independent things, even though they're both max and mins, right? So saying a function has an absolute max doesn't tell me anything about the relative maximums and vice versa. Questions about that? So the 4.1 is kind of laying out some theory that's going to turn into giving us kind of a powerful tool. And the theory comes in a couple theorems or statements that we do end up proving or talking through. I'm not going to go through those proofs here. They're done, well, in the book, but I think it's hard to read through the proofs in the book, but they are also done on the the lecture capture. So I would encourage you to watch those. But the basic idea, the result of those theorems is that an absolute extrema well, okay, sorry, I jumped the gun here. If f of x is continuous on a closed interval, and we spent some time defining what that means, continuous on a closed interval, you want to imagine it's got like solid endpoints, and there's some line that goes between those two endpoints, right? It can't have jumps or hops. It's a fine mental description. We know continuity is a little bit more subtle than that, but that's good. So if we have a function that's continuous on a closed interval, then it has an absolute max and a min. And this is called the extreme value theorem. So, and this is important because, oh, you've seen above here, here's a function that doesn't have an absolute minimum. And we can see it's because of this discontinuity, this asymptotic behavior. Just because it's discontinuous doesn't mean you don't have absolute maximums and minimums. You're just not guaranteed it anymore. If you have a continuous function on a closed interval, then you've got to have an absolute maximum and minimum. So that's useful. If we have the right kind of function on a closed interval, we know there's an absolute max and min. And our job is to try and find that max and min. And that's important because we certainly care about what the biggest and smallest values are. Remember, these functions can represent profit or quantity of drug in a bloodstream or efficacy of a vaccine, right? These are like, those are functions. Those are things that can be described as functions. And so we'd certainly be interested in the minimums and the maximums of those functions, right? And that is, in some sense, this maybe the most valuable thing about differential calculus is finding these maximum and minimum values. When you have a complicated formula of a function, it's certainly not clear where that max and min is. And so we're getting at the theory behind that. So the first thing is to say, okay, these have a max and a min. And then the second thing is to say, well, where could the min and the max be? So the extreme value theorem tells us when we know we have a max and a min. We also have one called Fermat's theorem, which says if f of a is a relative extrema, then f prime of a equals 0 or does not exist. Sorry for the mess there. F of a is a relative extrema. So what this is saying is, if you have a relative min or max, it turns out that the only way you can have a relative min or max is when the derivative equals 0 or the derivative does not exist. And visually, this does make sense, at least in specific examples, because, you know, if you have a function that looks like this, right, there's a relative maximum, and certainly that is a spot where the derivative is 0, right? The slope of the tangent line there is 0, and that is giving us a relative maximum. It's not totally clear that maybe there's like some other way of doing that. But it turns out any way you do it, the derivative is either going to be 0 or it might not exist. So if you have a discontinuity there, then it certainly could be a relative extrema, but then the derivative wouldn't exist either. So this is kind of, think of this as like shrinking the possibilities. It's not guaranteeing us that we have a relative extrema where the derivative is zero or does not exist. We can certainly have situations that look like that, right? There's a spot where the tangent line is zero, the slope of the tangent zero, but that's not a relative min or max. So it doesn't go the other way, but we can't just have a relative extrema, a min or max out of nowhere. It has to occur where the derivative is zero or does not exist. And so if you kind of take these ideas together, what we get is something called the closed interval method. And this is the example I wanted to make sure to show you. This is 4.1, kind of the biggest idea in 4.1. Find the absolute extrema of f of x equals, say, x cubed minus 2x plus 3 on the interval. Actually, let me make that, let's go minus 12 x plus 3 on the interval 0 to 3. So let's talk through this, and then we'll see if there's any questions, and that'll get us through the biggest idea here. Notice this is a polynomial, so it's certainly a continuous function, and we're looking on a closed interval. So that tells us by the extreme value theorem that there is a min and a max, an absolute min and a max out there. And that's important. If I don't know, if I'm not guaranteed of a min or a max, my theory and this method won't work. So luckily, most of the functions we work with are continuous on their domain. So we want to check that, but it turns out that most of the time we're safe. So there is a min and there is a max. Now, the question is, where could a min or a max occur? And it turns out it's kind of limited. A min or a max, from these examples, now this is not a proof, right? There's a more detailed proof given, but from these examples, you can see one possibility is at an endpoint, right? Sometimes an endpoint is the minimum or could be a maximum. If it's not an endpoint and it's a maximum, an absolute maximum, it turns out it also needs to be a relative maximum. Because if it's not an endpoint, then we can compare it to both sides, and if it's an absolute max, it's by definition also a relative max. So it turns out that an absolute max or min can really only occur at two types of places. It can occur at the endpoints, or at relative extrema. But relative extrema only happen where the derivative is zero or does not exist. And those we are going to call critical points. Critical points. Where f prime of x equals zero or does not exist. So what I have is I have a limited number of points to choose from. I have two endpoints here. So f of 0 could be the absolute max or absolute min, and f of 3 could be the absolute max or min. But I also have to worry about these critical points. Well, to find the critical points where the derivative is 0 or undefined, I take the derivative. This is a nice one, right? No complicated rules, just a nice polynomial. This polynomial is defined everywhere, so there's no undefined points, but it could equal 0 some places. So -2 and 2 are critical points. So those are values where there could be a local max or min, which means possibly an absolute max or min. These might not be local maximums or minimums, but local extrema couldn't happen anywhere else. I couldn't have one at 0.5 or 1.7 or the square root of 2, because those values are not critical points. They don't make the derivative 0 or undefined. And if you have a local max, a relative extrema, then the derivative has to be 0 or undefined. So what we've done is we've basically like sifted it down to we only have a couple possibilities. And it turns out here, because I'm looking between 0 and 3, I don't have to worry about -2. That's not in my interval that I'm interested in. I don't care what's happening to the function outside of 0 to 3, but I do care about 2. Now, these are integer values just because they're sort of easier for us to work with, but there's no reason the critical values couldn't be things like 1/2 or the natural log of 3 or values like that too. And so all I have to do at this point is figure out which of these is the max and which of these is the min. I'm guaranteed of a max and I'm guaranteed of a minimum, and I know these are the only places that I can, where they can occur. So to figure it out, I just brute force here. I plug this value into the function. F of 0 is 3. F of 3 is that 27 minus 36 plus 3, that's -6. And F of 2, what's that? 8 minus 24 plus 3 is -13. So absolute max, absolute min. It's actually pretty powerful stuff. I would encourage you to watch the lecture capture and look through the small videos on 4.1 to really keep working on the theory behind why this works and why we can reduce it to this this process, this closed interval method. But the nice thing is you can still do the closed interval method even if you're a little shaky on why that works, right? You can focus on the derivatives where the derivative is 0 and the endpoints and pick the biggest and smallest. Okay, it was kind of a lot of talking, right, for just coming off of spring break. But are there questions about that process, that closed interval method? Once you get the idea of it down, it will be fine. The challenge then will be as your function changes and you take its derivative, you will sometimes have some challenges in solving where it's equal to 0. So if it had a sign in it or a natural log function, those may become a little harder to solve for. So look for that, but the process is the same for all of these. If the question just asks you for the critical points, then you would, right, just have to figure out where it's 0 or undefined. So I would, my hope is that you'll be able to complete that 3.10, well, by tonight, because that's when it's due. I don't think there's 1 or 2 problems that may take a little time, but the others should go pretty straightforward. And then as you work through 4.1 for Thursday, I'm guessing or hoping that you'll come with, a question or 2 about some of these derivatives or critical points, which will probably be algebra questions, right? Like how do you actually solve some of these when you take the derivatives? Of course, to be able to do this correctly, you have to take the derivative correctly too. Some of them are very easy, like this polynomial. None of them are as hard as the messy ones we saw, you know, on the test or anything like that. But you have to be correct with your derivative, or else everything else you do is going to be off track. We don't want that.